Good morning, students. Today we are continuing to discuss power amplifiers. You can see on your screen the last page of our last lesson where we were discussing the performance of power amplifier, performance of common emitter amplifier, signal amplifier as a power amplifier. And the conclusion was that these signal amplifiers are very poor as a power amplifiers because their maximum efficiency is only 25%, right? We now go to the next step of actual power amplifier. We now are talking about a class A power amplifier with choke coupling. Class A means you remember the class A power amplifier means where the transistor conducts for the entire cycle of the signal, entire period of the signal. Now this is a choke. Here the collector resistor RC is replaced by a choke. Now I hope you know what is a choke. I think you have heard the name choke also. To give you a practical example, you have seen tube lights. In the frame of a tube light, you must have observed there is a small steel box. Within that box, there is a iron core coil. Actually, it's a inductor of large value. That's why it's an iron core. And since that choke in the tube light is working on 230 volt AC, so it looks heavy. So choke is actually a large value inductor, and in order to give a large value, it needs a core. Now, for audio signals like this, that core cannot be iron core because the hysteresis curve of iron does not suit the audio frequency. So, this core of these audio frequency chokes are ferrite cores. So, these are actually a heavy high value inductor. And since it's an inductor, it has got a very high AC impedance. So AC current does not flow through this. But for DC current, that means quiescent current, this choke is actually virtually a short circuit. Right? That's why I said, which offers infinite AC resistance and zero DC resistance. As a result, the entire collector, transistor's collector AC current, it cannot flow in this direction to common. It flows only in this direction. That means the entire output signal current flows through the load only. Nothing is lost in the collector resistor RC. That is the idea. Now, see how it works. We apply Kirchhoff's voltage law in this collector emitter circuit. It shows that VCC is equal to VCE plus ICRE because there is no resistance here, so there is no drop. So this is the DC load line equation. Obviously, the equation shows the DC load line intersects VCE axis at VCC and IC axis at IC axis. IC axis, because IC axis it will intersect on VCC. VC is equal to 0. Intersects IC axis at VCC by RE. So this red one is the DC load line. It intersects current axis in VCC by RE and the voltage axis at VCC. In fact, slope of this curve is 1 by RE, which is a very high slope. Actually, this curve, practically, it is actually almost a perpendicular curve like this. But if I draw a perpendicular curve, this line goes out of this picture. So I have purposefully given it an inclination. It is almost a perpendicular curve with a very little slope. Next is, now you apply Kirchhoff's voltage law for AC signal. If you apply Kirchhoff's voltage law for AC signal, this branch is open circuit because this is a very, very high AC impedance. So this is VCE Small VCE means AC signal VCE, AC current drop, AC potential drop across the collector emitter. VC, this is the positive direction, and this is the IL conventional positive direction is this way. So these are only conventional directions. Actual value will become negative or positive depending upon the real values. So this curve shows, this branch shows that VCE is equal to ILRL. Now, actually, collector current flows in the opposite direction, in this direction. But conventional load current is in this direction. So it is equal to minus ICRL, right? Then, so AC load line equation. Now, AC signal VCE is equal to total VCE minus DC part VCEQ. Similarly, AC current IC is equal to total current minus of DC portion ICQ. So this is an expansion of this earlier equation only. Now, for maximum current swing, this is the AC load line. And for maximum current swing, what do you want? This IC, the total current will be twice of ICQ. That is the basic principle from here. ICQ is chosen in such a way that the total peak becomes equal to that. So value of ICQ is equal to double of value of IC is equal to double of ICQ when VC is 0. That is the principle of choosing the intersection point of the load lights. So if we put this value here, VC is equal to 0 and IC is equal to twice ICQ. Then so 0 minus VCEQ equal to minus twice ICQ minus ICQ-RL. So this becomes ICQ, this becomes 2 ICQ minus ICQ becomes ICQ, and this is minus VCEQ. So ICQ is equal to VCEQ by RL. So here, by intersecting the DC load line and AC load line, we are finding what is the value of, what is the bias current ICQ. Now, putting this value of ICQ in this DC load line equation, what do we get? VCC is equal to VCE plus ICQ-RE. In that case, VCE becomes VCEQ. So this is equal to VCQ plus, now ICQ is equal to VCQ by RL. So it is VCQ multiplied by RL plus I by RL. So what do we get? VCQ is equal to VCRL divided by RL plus RE. And ICQ, and then ICQ is equal to VCQ by RL. So this by RL, so ICQ becomes VCC by RL plus RE. So here what we are getting is the desired or intended value of VCQ and ICQ. Once we have these values, we can go to next step of power calculation. So this DC load line equation, AC load line equation, and the values of VCQ, ICQ is repeated here for so that you remember what were the values. We can find out the point of intersection of AC load line and the VCE axis. That means the blue line and the VCE axis by putting IC is equal to 0. By putting IC is equal to 0 in the AC load line equation. In this AC load line equation, you put IC is equal to 0. Then VC minus VCQ is equal to IC equal to 0 minus ICQ minus RL. From this, we get VCE. That means this value is equal to VCQ plus ICQ RL. VCQ value we already know from here. ICQ value we already know from here. It becomes 2 multiplied by this. And if you ignore RE, this becomes 2 VCC. That means AC load line intersects the x-axis VCC, where DC load line intersects the axis at VCC. So this is the first part of going into power calculation. Then we can start power calculation. Now, what is the power drawn from the power supply from here? You know, it is the DC power, VCC, DC voltage VCC, multiplied by DC current ICQ. Now, ICQ we know from here, so we get it is VCC square by RL plus RE, which is approximately equal to VCC square by RL. This is the power drawn from the battery. Next is, what is the power delivered to the load? You remember in our last day's lesson, AC power delivered to the load is ICP square RL by 2, whereas ICP is the peak value of this current wave. This current wave from here to here, and for maximum swing, ICP is equal to ICQ, right? For maximum swing, ICP max is equal to ICQ. So if we put ICQ here, if it is ICQ square by RL, now put the value of ICQ from here to here, it becomes PCC by 2. That means power delivered to the load is half of the DC power drawn from the battery. You remember, this ratio was 1/4 in common emitter amplifier. In common emitter amplifier, the maximum power it can deliver to the load is power drawn from the battery divided by 4, right? Whereas here, it can deliver power drawn from the battery divided by 2. That means double of your common emitter amplifier. So this is how a power amplifier works. Now let's see what is the power dissipated in the BJT. Power dissipated in the BJT, you recollect this equation. Power dissipated in the BJT, PT is equal to PCC, is the DC power drawn from the power supply, minus ICQ square RC plus RE, that is DC power lost in the RC and RE, minus the AC power delivered to the load. So power cannot vanish. So the total power is this drawn from the battery, out of which some part is lost in the transistor as a heat, some part is lost in the RC, RE collector emitter resistors, and the remaining part is delivered to the load. Knowing this, here the collector resistance RC is 0. Here collector resistance RC is 0. So what is PT? PT is equal to PCC minus ICQ square RE minus this load power. Or PT is equal to the PCC value we just found out in the last page. It was VCC square by RL minus this RE we are ignoring, is a very, very small power. So PCC is VCC square by RL minus the power delivered to the load, right? Now what is PT maximum? That means when the transistor is hottest, maximum power lost in the transistor. It is when this is 0. That means when signal is 0. The same was the case in emitter follower, common emitter amplifier also. And when this is 0, the maximum power lost in the transistor is VCC square by RL, which is equal to PCC. That means this is a very, very noticeable situation. That means if you have a choke coupled amplifier and you have switched it on and there is no audio signal, that means you have not yet connected the mic or record player or anything, then the entire power drawn from the battery goes in heating the transistor. So the transistor will become very, very hot. So for choke coupled amplifier, it is not at all. And I said earlier, for any power amplifier, it's not advisable to switch on the power unless there is a signal. But for choke coupled amplifier, it is all the more necessary. That means the entire DC power drawn from the power supply is lost as heat in the BJT. Then what is the efficiency of this? Efficiency definition is the power delivered to the load divided by power drawn from the battery. Power delivered to the load is ICP square RL by 2 and power taken from the battery is VCC square upon RL. This is equal to this, right? Now, when is efficiency maximum? It is maximum when ICP is maximum. And what is the maximum value of ICP? Look here, ICP, the signal can goes up to this and this. So maximum value of ICP, that is the peak value of the load current, is equal to ICQ. And we know the value of ICQ, it is VCC by RL. So this is 50%. So maximum efficiency of a choke covered amplifier is 50%, whereas it was only 25% in common emitter amplifier. So you see another big improvement in this choke coupled amplifier. Here is the power consumed by the transistor under any condition, and that happens when signal is zero. And this is maximum load power delivered to the load, and this happens when signal is maximum. If you make this ratio is 2. And this ratio in common emitter amplifier was also 2. That means in both cases, if you want 1 watt signal power, then you must purchase a 2 watt transistor. AC power to be delivered to the load, the transistor must be 2 watt. The same was the case in common emitter amplifier also. But what is the benefit of choke coupled amplifier? Amplifier will draw only 2 watt power, whereas the basic common emitter amplifier will draw 4 watt power because their efficiency is double. And this is the curve for choke coupled amplifier, where this is this is the PCC, power drawn from the battery. This is always fixed irrespective of your signal. As the green line is the signal, as the signal increases, then this output power increases. And at the same time, the blue line was the power dissipated in the transistor. So when the signal is zero, all power is dissipated in the transistor. As signal power, output power increases, the transistor heat decreases. So the more and more signal is given, transistor becomes less and less hot. And the efficiency also rises up from 0 to 50%. So this is a choke coupled amplifier. After we have learned the choke coupled amplifier, we come to another class A power amplifier, which is transformer coupled. Now, this transformer coupled amplifier is very, very common audio amplifier. I think if you open the box of any audio amplifier in front of you, you will find at the output there is a transformer like this, right? Now, what is the beauty of this? AC power delivered to the load, we know in earlier, is proportional to the load resistance, RL. And our so far load resistance was connected here through a capacitor to the ground here. RL was connected in this line here. So if RL is more, then output power delivered is high. And also efficiency is proportional to RL square. So we want RL is very high. But in an audio amplifier, or wherever is an audio output is always a speaker. And speaker impedance is normally very low. It is something order of 4 ohm to 16 ohm only. That is a problem of designing audio power amplifier. In that case, this resistor is considered this is a speaker which has a resistance RL, is connected to the transistor collector through a transformer. Now, what benefit does it give? It's like this. Say turns ratio of this transformer is n is to 1. That means here the number of turns is n, here it is 1. Right? And let us say VC, all VC is the AC voltage developed across the primary. Right? AC voltage developed across the primary, and VL is the AC voltage developed across the secondary. So you know the transformer ratios. If it is N and this is VC, this will be VC divided by 1. But current will be VC IC multiplied by N. Anyway. And let's say VL is the secondary voltage developed across RL. And RL is the impedance or resistance of the speaker coil. Now, by the ratio of transformer, this current in the primary will be nth part. That means secondary, since secondary coil number of coil is less, its voltage will be less, but current will be high. So this current in the primary IC is 1. Let us say our RC or RL was always connected to the transistor collector. So we want to find out what resistance this collector finds in place of RL. What is the equivalent resistance of RL if it is placed in the collector circuit? Let's say that resistance is RL dash. Now, by transformer relation once again, RL dash is equal to VC by IC, collector primary voltage by primary current. And primary voltage is N times secondary voltage, and primary current is 1 upon N of secondary current. So this makes equal to N square RL. This is a basic transformer relation, which is not a part of communication engineering. It's a part of basic electrical engineering. I hope you remembered that. The impedance of the secondary is reflected in the primary N square times, where N is to 1 is the coil ratio, turns ratio. Now, it becomes very simple. Now, it is a simple common emitter amplifier with load resistance equal to RL dash. RSC is equal to RL dash, and RDC, for the DC current, only resistance is RE, and AC resistance is RL dash. With this concept, with this conclusion, this becomes a simple common emitter amplifier. There is nothing else. And we know quiescent point of this common emitter amplifier is given by this relation I have discussed long time back when I was discussing biasing circuit, self-biasing circuit of the common emitter. Self-biasing circuit of the common emitter, it gives the relation that quiescent current ICQ is VCC, this power supply voltage, divided by RAC plus RDC, and VCQ is equal to VCC RAC divided by RAC plus RDC. Because so it is quite easy to remember. Both of the denominators are same. Only voltage is multiplied by RAC. With this relation is here. AC resistance in this path is only RL dash. DC resistance in this path is only RE. ICQ is this much. VCQ is this much. Now, then, what is the value of ICQ then? ICQ is, we put this value of RAC, RDC. ICQ is RL dash plus RE. If you ignore RE, this is VCC by RL dash. And what is VCQ? is equal to VCC RL dash divided by RL dash by RE. Once again, if you ignore RE, it becomes only VCC. So we find the quiescent current is VCC by RL. This quiescent current here is only VCC by RL. And quiescent voltage VCQ is actually equal to VCC. But here we have shown two different lines because otherwise the drawing becomes very clumsy. As I said, this red DC load line is almost vertical. And there is a slightly difference. If we do not ignore this RE, then it becomes slightly different. If we ignore RE, then practically you consider VCQ is at VCC only. Now we start power calculation. What is the power drawn from the power supply? Is the voltage of the power supply multiplied by DC quiescent current. DC quiescent current is given here, so it is VCC square by RL. Simple. Then what is power delivered to the load? Once again, the same relation, ICP square RL dash by 2. And what is the maximum power delivered to the load when ICP is maximum? And what is the maximum value of ICP is twice ICQ. What is ICQ is only VCC by RL. So it is ICQ, so it will be VCC square by RL into RL by 2, which is VCC square by 2 RL. Fine. So we have got the power drawn from the battery. We have got what is the power delivered to the load. And what is the maximum power delivered to the load is VCC. What next is what is power dissipated in the transistor as a heat? Power dissipated in the transistor as a heat from that other equation is also the power drawn from the battery minus power delivered to the load. There was another item, that is power lost in the emitter resistor, which is very small, which we have ignored. Value we have got here, and PLAC value we have got here. When is transistor power maximum? It is when this is 0, when signal is 0. That means maximum power dissipated in the transistor is VCC square. Then all these values I have written here. We got ICQ, we have got VCQ, we have got PCC, we have got PLAC, we have got PLAC max, etc. And what is the maximum power dissipated in the transistor? With this, we calculate the figure of merit. Efficiency is power delivered to the load divided by power drawn from the battery. Power delivered to the load is this thing here, and power taken from the battery is this thing, it is here. So it is this relation, fine. Then when is efficiency maximum? That is when ICP is maximum. That means the peak of the collector current is maximum. And what can be the maximum value of the peak of the collector current? It has to be equal to. So maximum of this peak cannot be more than ICQ. So in place of ICP, we put ICQ, and the value of ICQ is taken from here. Right? So if we find it 50%. So maximum efficiency is 50%. It is same as the choke coupled amplifier. So maximum efficiency of choke coupled amplifier and transformer coupled power amplifier is same. Figure of merit also, maximum power dissipated in the transistor VCC square by RL, and maximum power delivered to the load is this is also 2. Now this figure and this figure same as choke coupled amplifier. Thus, power performance of transformer coupled amplifier is exactly same as that of the choke. Then why do we need two different type of amplifier? The reason is Main reason is the matching of the speaker with the stage of the audio amplifier. That is the main reason. In fact, if you in your laboratory project, if you try to design a power amplifier, you will definitely at the end land up with this situation where you need the matching transformer. And matching power transformer is not at all difficult to get in the market. It costs hardly, nowadays it may be hardly 100 rupees. And the shopkeeper will ask you, what is the speaker resistance? You have to first get the speaker. Speaker may be 4 ohm, 8, 6 ohm, 12 ohm. You tell the shopkeeper, my speaker is 4 ohm. He will automatically give you a matching transformer. So this is class A power amplifiers. So what we have learned at the beginning, last lesson we have learned what is a power amplifier really. Then we learned how our common emitter signal amplifier works as a power amplifier. We found it is worthless. Then, but why did we learn that? We learned the method of power calculation by using the common emitter amplifier. Otherwise, it would have been very difficult. Once we found that common emitter amplifier is worthless, then we designed the choke coupled amplifier. Then we designed the transformer coupled amplifier. So this is where we end the class A power amplifier. In our next lesson, we shall study class B power amplifier. Then for the next lesson, we shall study class C power amplifiers. Okay, we finish it here. And once again, my request, students, if you are in a good mood, please subscribe to this channel so that I get some interest in continuing this effort. Okay, bye then. Bye.